Hi, so this will be my video for MCQA. So right now, 3 out of the 6 of you have completed MCQA. It looks like the other 3 are currently working on it. But I chose 3 questions that those 3 people that finished all got wrong, and I'll talk a little about them. Here's the first one. So a point on a rotating object has an initial angular velocity and rotates with an angular acceleration from a time interval from t equals 0 to time t equals t0. The point then rotates at a constant angular speed until time t equals t1. What is the angular displacement of the point from t0 to t equals t1? So all the way from 0 to t1. Express your answer in terms of the following constants. So the only really key thing to note here is not only do you have a time where you have an acceleration, you have a time where you don't. So you have to apply 2 different equations here to get this to work. So here's our constant acceleration equation. So this can be used whenever there's a constant acceleration. Of course, there are other 2 equations that are similar and used with different variables. And then we have our constant velocity equation, which looks like this. And the only one that utilizes some equations from both constant acceleration and constant velocity would be the last one. So that was the real key in this problem. So let me erase out this. We'll go to the next one. Right. Here's our next question. So we have a graph. Time versus net force. Which the interesting thing about this graph is you wouldn't be expecting a rotation problem with this graph, but certainly a momentum problem, but a linear momentum problem. Because here isn't torque, but force. So there's something weird going on here that we need to focus on. So a net force is applied to the edge of a disk that has a diameter of 0.5 meters. The disk is initially at rest. A graph of the net force as a function of time for the edge of the disk is shown. The net force is applied tangent to the edge of the disk. How can a student use the graph to determine the change in angular momentum of the disk after 8 seconds? So change in angular momentum is this equation. And then, of course, we have to define torque. This is tangential, so we don't have to worry about sine theta. So I need to take into account the radius and the force to give me torque. The force is 3. My radius is 0.25 times by a time of 8 seconds. The area under the curve, except that I have to take into account what the radius was, because this is angular momentum. And then we come to this answer: determine the vertical intercept force, multiply by the radius, and then multiply the result by 8 seconds. This procedure can be used because change in angular momentum equals torque times time with torque equals RF. Great. So I'm going to stop this video here, and then we'll do one more with question 20.